talk here about new issues, unpublished stuff in IPv6. Yeah, my name is Marc. I've been around for something like 17, 18, 19 years, so I'm one of the old dogs. I believe that hackers doing security research, writing tools, publishing vulnerabilities is critical for the security of systems and also to protect privacy data. So it was always very important for me to look at stuff. It's important for infrastructure. It's important for data to be protected. So over the years, again and again, this has been IPv6 for me. There's more stuff I do, lots of the stuff I can't talk about because it's for customers. But it seems that nobody else is really doing IPv6. And that is kind of sad, because that's what we will all have in the next 5 years. And if there is really nobody looking at that and looking for vulnerabilities and pushing and kicking the vendors to do better because they're really not doing well, then we will have a very bad state. So that's why, for me, IPv6 is so important also. I'm doing it for that long time already. It's boring as well. But yeah, here I am with my third installation of completely new stuff for IPv6. Initially, I didn't want to do a third installment. But Dylan really pressed me, so, hey, please come to Hack in the Box, please present. Oh, I don't care what you do, but please do talk about your stuff. Yeah. I'm too determined that I wouldn't just rehash old stuff. So everything in this talk is completely new. I think a lot of people are not looking into IPv6 because they think, everything in IPv6 was already found and discovered, and there's just very little things, and there is not more you can do for research. So in that third installment now should show again that there is still lots of stuff to research in IPv6, and it is really necessary. So this talk is really a potpourri of things. There is nothing like a red thread. We'll be talking about vulnerabilities. We will be talking about problems of installations which are there, so bad configuration stuff. And I will also show you about penetration testing, how to do remote penetration testing. And if there is still time, I will talk about the, let's say, not so much security, but the issues with IPv6, why it is very difficult to deploy at the moment. So first, I want to show you something about the current situation. So why should you, or why should we care? Once upon a time, that was long time ago, IPv6 was designed, was the first standard, the first RFC published was 1995. That's a long time ago. So, and when it was seen, okay, the IPv4 address is shortly depleting in the far future, that's when already ripe organizations, IETF and others, and even governments, were trying to push IPv6 slowly, and then stronger and stronger and stronger. And it was hoped that it would look like that, because the IPv4 pool size would become empty slowly. People would adapt and start deploying IPv6 early, so not running into any trouble. That was everybody was thinking what would happen, what everybody hoped. But the reality now, today, is this. The IPv4 pool size is in a critical state, but the IPv6 deployment is meh. Yeah, so this is really a big problem for our infrastructure now. 3 weeks ago, or 4 weeks ago already, RIPE, that's the European registration for everything IPv4, everything IPv6, DNS and stuff, they announced that they only have one Class A network left to hand out IPv4 addresses. And with that, a special protocol kicks in. Nobody can get new IPv4 addresses unless they prove that they have already started to deploy IPv6. So without proving that you are deploying IPv6 at the moment, you will not get more IPv4 addresses. And actually, there are, you could say, one Class A network, that's a lot. Just 1 month before, they were expecting that the rest of the IPv4 addresses in Europe, until they hit this last level, it would take several months. And it was just several weeks. And it looks similar in all the other regions. If it's Asia, if it's the US, so North America, Africa, South America, it's all the same. It's just Europe which was hit first. But all others will follow very fast. So in other words, the end is very near. So that's why you really have to scramble now and start deploying IPv6, because otherwise there is no growth possible on the internet. And we'll hit a limit, and this will be bad for business, this will be bad for everybody. Everybody of us has not one device, one laptop, but maybe now you have your smartphone and you have your tablet also. Yeah, you need more and more IP addresses. So even there can't be new growth if we don't go IPv6. So that all could be very nice if it would not be that the security issues in IPv6 wouldn't be so, how should I put that nicely? It wouldn't be so bad, so fucking bad. If you look at the registered vulnerabilities for IPv6 over the years, you will see this is getting more and more. Why is it getting more and more? Because in the beginning, there was not much implementation of IPv6. There were not many people looking into IPv6, so there was not much to be found. But as more and more systems get IPv6 implemented, get more features of IPv6 implemented, more people look at it, of course, more vulnerabilities are found. This is not showing the full picture. This is just the current state, and these numbers are actually, I think, 2 weeks old now, or 3 weeks old now. So how this works is, and I have this slide in every presentation I do about IPv6, so it's constantly updated. We are already in the beginning of October. We're just about half what will still be published with a 2012 CVE entry. Because if you find a vulnerability, usually you register it, you inform the vendor, but you're not publishing your CVE number until there's a fix. And if you work with companies like Oracle, this can take some years. So even today, there are bugs which are not being published to 2011. And it's not just 2, as it looks like here. It's in reality way more. And if you say, wow, this guy is pretty optimistic or pessimistic, depending on how you look at that this many vulnerabilities will come, well, this presentation alone will show you 6 new vulnerabilities in IPv6. Well, actually, how CVEs are counted, actually it will be rather like 8, 9, 10, because they do it per implementation in operating systems. And also, I think 1 or 2 weeks ago, I saw that someone was releasing vulnerability information he found in DHCP version 6 implementations. So someone wrote a fuzzer, tested implementations, and it was breaking left and right. So that was another 4 CVE entries. So that all alone already gives you 12 more. Yeah? So we are already here. So this is not true, and it will be way more for 2012. So what are some vulnerabilities? And first, sorry, I forgot that one. You might say, okay, we have IPv6, what about IPv4? IPv4 is also vulnerable, and there are bugs and stuff and that, so where's the difference? The difference is that also there's more IPv4 deployed, and IPv4 also has wide coverage, and people looking at IPv4, the numbers of vulnerabilities found in IPv4 is just half the numbers. Also, there's less IPv6 in the system than there is IPv4. So you see, there is a difference in maturity when it comes to security in IPv6 implementations. So, some vulnerabilities. I categorized in a bit. The first are I call flooding surprises. So people not expecting something could come from that kind of direction. The first one is actually just a reminder. 2 years ago, I was when I did the second installation on stuff in IPv6 you should care about, I announced the vulnerability which was called router advertisement flooding, where there's a feature in IPv6, and you might notice I'm not doing an introduction to IPv6. So if you don't know IPv6 already, look at my first and second installment of the talks. You will find introductions there. I don't have enough time because I have too much to cover here, so I left that out. Auto-configuration is a feature which is trying to replace DHCP. It runs on the network level, so ICMP-based. And this auto-configuration feature means, yeah, systems configure themselves an IPv6 address automatically. So if you swamp the networks with router advertisements which force the systems to do auto-configuration, they try to configure themselves 1 million IPv6 addresses, and of course, this can't work, and yeah, all the systems crash. So that was 2 years ago. It affected all Windows systems. It affected Cisco. It's Juniper NetScreen, FreeBSD, NetBSD, old Linux. And most people fixed that, except Microsoft. So you can crash any Windows systems, even the new Windows 8 and Windows 2012 server. You can crash if you're on the local LAN. So here at the conference, the IPv6 would be working here. They tried to make it work, but there is a bug in the IPv6 controller. That's why they had to disable IPv6 again. So the packet type is not coming through. If the bug would not have been there, I would have showed that to you. And then all your system would be unusable, forcing you to complete a reboot. And that's a bug Microsoft is not fixing for 2 years, over 2 years now. Last year, I did some more router advertisement stuff because this is a, let's say, you can do lots of stuff with router advertisement, and I found another denial of service you can do, not via auto configuration, but what you can also do in router advertisement is say, okay, these are routes you should put into your routing tables because I'm also responsible for these network destinations. And you can put as many as you like in a router advertisement packet. And if you do that, the systems all have to update their routing tables. And that's what they do if you send that. Memory consumption, 100%, CPU, 100%. And you might be surprised, that's basically the same systems. So 2 years ago, a very similar bug, okay, I understand this is a problem, I fix it. The same issue, pretty much still there, which shows that they're not really thinking about what could go wrong in IPv6. If a very similar, so totally similar bug is still there. So the package is already online. Sadly, as I said, IPv6 is not working here in our conference network. Otherwise, you could have lots of fun. This is a tool. You see how easy it is to use. If you run that, everything BSD-based, every Windows system is just gone. The BSD systems recover when you stop the attack. Windows is crashed, there's nothing you can do. But the BSD systems recover. They seem to have recovered. However, IPv6 is not working afterwards. You still have IPv6 addresses, you still have IPv6 routing entries, but if you try to do anything IPv6, it just doesn't work. So weird bug which that triggers. Another flooding issue is what I call neighbor solicitation flooding. Neighbor solicitation in IPv6 is replacing ARP, Address Resolution Protocol, what we have in IPv4. Because it was deemed ARP is ugly. We're trying to solve an IPv4 problem with an extra protocol that is not IP, but ARP. That's why in IPv6, address resolution, so MAC address to IPv6 address relation, is done by ICMP. And the mechanism for this is neighbor solicitation. So when you need the MAC address for an IPv6 address, you send a packet on the network saying, hey, I need this I want to connect to this IPv6 address. What's the MAC, who has the MAC address for that? And the system, or anybody could answer, but usually on a nice network with nice people, only the real system who has this IPv6 address will answer with a neighbor advertisement and saying, hey, yeah, that's me, and this is the MAC address you should use. This is how it works. However, as I said, flooding, surprises coming from direction you haven't thought about. If you start flooding the destination with neighbor solicitation packets, what happens is that the kernel is busy, because this is done all in kernel level, that the system is so busy sending neighbor advertisement, you can't do anything else with the system. Yeah, I thought, okay, when I thought about, okay, this could be an issue, let's try it. Again, I was surprised who is affected. It's Windows, it is Solaris, it's OS X, it's FreeBSD, NetBSD. Lots of systems, I mean, come on. Is this elite hacker work? This massive, super secret, complicated vulnerability, like, for example, the previous speakers here showed you with iOS 6, how to exploit that? Come on, this is baby work compared to that. Yeah? So it's a shame that this stuff works. But that's the state of security in IPv6. We're still in a medieval age in IPv6, although it should be a very modern new protocol which will need to depend on the next 20 years until that IPv6 space runs out and we need maybe IPv8 or something like that, which will have the same problems, I'm sure. So another thing, fragmentation surprises. Of course, IPv6 also has fragmentation of packets as they have on IPv4. There's a different thought. In IPv4, routers fragment packets. This is not allowed in IPv6. In IPv6, for various design reasons and philosophy stuff, only the systems themselves may fragment packets. There's a lot of stuff that can go wrong from that direction. So stuff which is surprising for people implementing IPv6. This is one of the 2 slides where you actually see something from IPv6 protocol. So this is done by an extension header. So in IPv4, you have options to the IPv4 header. In IPv6, you have a fixed IPv6 header which just contains what is really essential in the packet, and everything else which is kind of optional or nice to have, a feature. These are extension headers which are in between until you get to the transport layer, which is TCP, UDP, ICMP. So one of the extension headers is a so-called fragmentation header. As it is a chain, it specifies what the next header would be, which could be TCP, UDP, ICMP. Always has a length of 8 bytes. It has a fragmentation offset. This specifies where this fragment should be when the packet is assembled, where the data should be placed. So the first fragment, of course, always is fragmentation offset 0. And then there's a reserve bit, and there's a more fragment bit. If the more fragment bit is set, it means more fragmented packets which belong to this fragment chain are coming. Once this bit is not set, he knows, okay, the destination system, so okay, now I can reassemble the full packet and work with it. And so you can, and because in IPv4 we had the IP ID field, which is not there in IPv6 anymore, to know which fragment chains belong together, you have a fragmentation ID. So a fragment for a different larger packet has a different fragmentation ID, and so the systems know what belongs together and how to build it together. So stuff that can go wrong. So you create a large packet and you start sending it in fragments. So the first will start at offset 0. You set the more fragments bit, and for example, you send 1 kilobyte of the packet. You do it with the next, so the fragment offset is 1024, because you send 1 kilobyte of data. You send the more fragment bit, and so on. Until you get at 64,000 bytes 512, again setting the more fragment bit, and you send 1016 bytes of data. Why that? Because that sets the fragmentation offset to the maximum value possible. And in the last fragment, you set the more fragments bit to 0 and put the maximum bytes of data in there. What happens that this packet is now reassembled to a very, very, very large package with illegal because it's larger than 64 kilobyte. So together with the 40-byte IPv6 header, this packet is now reassembled 67,000 bytes large. And if you didn't think about that, yeah, bad things could happen. All the bugs actually showing you here now, I didn't look for them. They just happened to me. Really, lots of the stuff, usually I'm just interested in, hey, I have this idea, so I code it. And here I was playing, so let's check if I can do this kind of fragmented packets, how the system reacts, so just drop the packets whatsoever. And my system was constantly blue screening. And I was saying, wow, what the fuck? Actually, I didn't care a lot. So after a year of constantly my system blue screening, I said, oh, okay, lazy bastard, get down, look what the problem is. And after really some long debugging and testing and stuff, I found out, oh, it's the personal firewall I was running on my machine. Yeah, so via a personal firewall, if the packet passes the firewall so it's not blocked, this is what happens. Nice blue screen. It was just fixed last week, so the Avira personal firewall, which is available for download or for update 2013, has fixed this bug now. If you're not updating to 2013, so you're staying with 2012, which will be the case for, well, businesses who have Avira firewall deployed, they will have to wait for another few months until the fix is there for them, because they had to change lots of the stuff internal. So it was not easy for them actually to fix that. Yeah, more stuff, more fragmentation surprises. This is a successful sidewall firewall. Again, I was not looking for that bug. Yeah? And it's pretty weird. Let's say you have a sidewall firewall and you allow it from the external side to access the SSH port of a system. Now, this time, this is an evil hacker accessing that system because somehow is trying login password guessing or has a valid login password pair. So the administrator gets panicked and say, okay, I block, so it's allowed through. So the admin changes the rules in the firewall and say, no, no, I block this. I block everything to this machine, everything. Yeah, so nothing can happen anymore. And true, if the attacker wants to continue to connect to the machine, this is blocked by the firewall rules. Unless you put a fragmentation header before that. It's exactly the same. You're trying to establish a new connection, but the site will let that packet pass because they say, yeah, we originally in history had this rule, so there might still be established connections. And that's why I have to let this pass. But this is not an established connection. It's a new connection. It's a SYN packet. So it's not an established connection, but because everything which is fragmented must, for their logic, be an established connection and let it pass the firewall. And, okay, I mean, things can happen. I mean, surprise, surprise, okay, bugs happen. I can totally understand that. However, they don't consider this a bug. So you change the firewall rule to block something. It's working unless you do a little trick, but that's not a security issue. So they're not fixing that. A third thing for fragmentation surprises to really show you how simple something, again, this is an Astaro firewall, and in my test, it was just an innocent bystander that was just hit. So what I did, it was very, very simple. I was actually testing some customer equipment, specific stuff, and that was just on the path. So this real destination, I flooded with fragmented packet. So a fragment ID chain A, I sent an offset at 0, offset at 20,000, offset at 60,000. And, well, if an implementation is bad, they already try to allocate the whole memory required to reassemble the packet, even if there's a large gap in between. So by just sending a few of these packets, all the memory of that firewall is consumed. And it's just dead. Again, come on. This is such a simple attack. And it just goes boom. It might affect all the other firewalls on the market, I just know. As I said, I'm not really looking for that stuff. They just happen when I look at stuff. So as I said, innocent bystander. So, and it's just gone. The people from Astaro, they told me, yeah, that was actually Snort, which pulled the system down and let it crash. I talked to the people at Snort and told them, okay, this is my test case, this is the tools, can you please test that in your version, it's working? And they said, nah, they don't see that problem. So they tried it, but they're not affected. So either it's some special thing, they had an old version in the Astaro firewall, or it was not Snort, it was rather putting the blame somewhere else. I don't know, I don't care. Yeah, but that what happens. Then router alert magic. What is router alert? Router alert is an option in a hop-by-hop extension header. What is a hop-by-hop extension header? It's an extension header which says if this is present, every router on the path must have a look at this header and looks if there is important information for him, for that router. So every router of the path has to look at the extension header if there's a hop-by-hop extension header. There are various options you can have in this extension header type. One is the so-called router alert option. The router alert option specifies, hey router, I have information on the upper layer protocol, ICMP, UDP, TCP, which is important information for you. So you have to look at the contents of the transport layer. And here is the value type, and this specifies what kind of transport it actually is. 0 is, for example, multiclass listener discovery. There are more for rendezvous points and stuff like that. So this is router alert. Yeah, I was surprised when the following happened. But let's go directly to what's the issue here. If you ping a router, and that router has an ACL which forbids receiving ICMP from anybody, then, yeah, nothing will happen. The packet is filtered, done. The router is protected by the ACL. However, if you send, let's say, a ping, but any ICMP packet works, through a destination behind a router and set the extension header hop by hop with the router alert option, surprise, surprise, it reacts fully to that packet. So if you send a ping to a completely different system, that router will send the reply. And it works for all ICMP types. So you can bypass ICMP ACLs for a Cisco router. Not all iOS versions are affected, but, and that was why this was important for me to get fixed, my ISP was affected. And I want to have this bug fixed. And you might say, hey, come on, why do you want to have this bug fixed? Because of some other magic I found out before this bug was introduced in iOS. And this is, I thought there could be a nice denial of service possible. I mean, if you send a router alert packet and specify, hey, look at the transport protocol, what happens that the router must go from ASIC, so from hardware processing of the packets, to CPU processing of the packet. Because now it must copy the packet to the memory, the CPU must have a look at the packet, work with the packet, yeah, and that slows the machine down. So I was thinking, if I do put a router alert in packets, it will slow down the CPU of the routers on the path, so the packets will be slower, all packets through the routers will be slower. Yeah, nice denial of service maybe. To my surprise, completely the opposite happened. My packets were becoming unbelievable fast, unbelievable fast. For example, in my tests, because I couldn't believe that stuff, what I was seeing, I sent a packet to a faraway IPv6 server in Japan. So the round-trip time was 1.8 seconds. Pretty slow responsiveness over the whole internet to get to Japan and back to Germany. With the router alert option, it dropped down to 200 milliseconds. If you're into first-person shooters and stuff, speeding up the latency is really, really good. And there are, for example, for the ISPs in Germany, they'll let you pay that extra if you want a low latency on your DSL connection. And in the beginning, I was thinking, oh, this must be a bug. What I see as a result here, that can't be true. Yeah, there must be some bug in some system, and that's answering. So with Philippe, my good friend from France, he has a server which is IPv6 enabled in France, so I was doing this to his server. He sniffed with TCP dump, seeing that really the packet arrived at his machine, that his machine sent the reply back to me. I only received one reply, so really it is the case that you can really get a big speed increase if you set a router alert extension header in packets. I don't know why. For me, it doesn't make sense. The only explanation I have for that is that if there's a router alert, it gets immediately picked up, put into CPU, seen, oh, there's nothing I really have to take care about, put back to hardware, but jumping the packet queue in between. And that's why it gets so fast. That's my theory. I don't know if that is true, but that's why I want to get this vulnerability fixed, because my ISP upgraded his router to this iOS version, which is affected, so now this doesn't work for me anymore. That's why I want to have this fixed. Other topic, as I said, potpourri of different things. That was vulnerabilities where vendors fuck up. But it's not just the vendors fucking up when it comes to IPv6 security. People seem to think, for whatever reasons, that on IPv6, nothing bad can happen. I did lots of IPv6 scanning, and if you've done IPv4 scanning on the internet, you know you get into lots of trouble very fast. So you get lots of emails from abuse teams. Your ISP abuse team is kicking you and saying, hey, what are you doing, what are you doing, what are you doing? On IPv6, nobody seems to care. So I did a lot of IPv6 scanning. Over time, I found over 500,000 alive systems on IPv6. So I have good statistic data, but here I did something special. That was just a few months ago. So for this presentation, I did extra statistical research, new research. I selected the 2,500 largest companies, domains, which have IPv6. And what I did for these domains, I checked the names, the name server records, the mail exchange, so mail records. I did domain name hosting, for example, for web, www, FTP, SMTP, various service names. And every time an IPv4 and an IPv6 address was returned for an entry, I put these into a list. After I did that, I scanned these addresses. Again, nobody complained about that. That's very nice. And I wanted to know, how is there a difference in protection of these servers on the IPv6 internet? And, well, to surprise or no surprise, depending how much you know about IPv6, there is a big difference. So I looked for everything which is remote administration of servers. So VNC, RDP, SSH, Telnet, FTP. And yeah, for example, for SSH, 5% of all the servers were on IPv6 were reachable for SSH, but only 3% on IPv4. And all the other numbers also, they are way lower. IPv6 in the other areas has something like 10 to 15 to 20 times more open administrable services to you than on IPv4. So people not thinking about that something bad can happen. People seem to think hackers don't do IPv6. Then what I did next was, now that I had IPv6 enabled servers all over the world, I did a trace route to all of them and collected the IP information of all the routers on the path. So all of the ISPs all over the world. And I did the same thing, connected to SSH and Telnet and see, are there ISPs protecting their router equipment? And surprise, surprise, no. Even Telnet, come on, Telnet on an IPv6 router. That was something like 7–8% of all the routers on the IPv6 networks are connectable on the Telnet port. Come on, it's 2012, that should not happen. SSH, of course, way more, but look at the difference. 6% reachable on IPv4 on SSH, 17% on IPv6. People think IPv6 is still a nice place. Maybe it is. But you want to go for that risk. So people think IPv6 is not really a problem. If it's the vendor, if it's people having to actually implement infrastructures. Everybody seems to think IPv6 security, oh, what could happen? What could possibly go wrong? Yeah. So, another different topic. How do you remote pen test IPv6? In IPv4, this topic is covered and covered and covered. In my last installation of the talk, so the second run, I showed how you could find, because of the large address space you have in IPv6, how you could find systems if they have a common address configured. If you want to know more about it, just go on YouTube. You'll find the talk there, which gives you all that information. What is happening behind the scene, because here there's just one slide with a command on how to do that. But so far, there's no documentation on how you would do remote pen testing of an IPv6 network. The big problem with scanning IPv6 networks is that you have a default subnet mask of a /64, which means if the network, the IPv6 address length is 128 bits, that every subnet in the world, every small subnet even here, is 4 billion times the whole internet. 4 billion times the whole internet is the size of every subnet in IPv6. There is no way you can do a ping scanning on this address space, because even your grandchildren will not be alive anymore with this scan for this subnet finishes. Yeah? Not possible. So this is a big issue if, as me, you're a consultant and you perform remote penetration testing for customers. So that's why this is kind of, for me, an important topic to teach other people. It is feasible, also not as easy as an IPv4. So how do we do remote pen testing of IPv6? So how do we find the target? Because that's the essential part. Once you've found all the alive system on the remote IPv6 network, everything stays the same like an IPv4. Then you do nmap port scanning, then you enumerate the services, then you try to find for misconfigurations, weak passwords, and so on and so on. But you must first get there. You first must find the systems that are alive on the remote network. So how do we do that if the networks, the subnets are so large that you can't scan them? Because there's nothing like a broadcast address you can just ping when you pick up some systems. That's not possible in IPv6. So thank you, RIPE, because I wanted to do this really hands-on, real world. And this was the organization I found where every kind of what you can do to do this works on. So everything I will show you now, if you want to try this again, it works at RIPE. Some stuff doesn't work on some companies, others works on others, doesn't work there, but here everything works. So it's an ideal candidate to show this is what could possibly go wrong. They might not be happy with me showing that, but it's all legal. They can't do anything about it except securing their systems. So thank you, RIPE. If you look into, for example, RIPE, what is in the registered address space for a target, the address space they have is usually very large, and they might have many address spaces actually registered. But not everything that is registered as IPv6 address space for a target is actually used. So if the target is large enough to have an autonomous system, so having 2 ISP connections running BGP, what you can do, you just look for the autonomous systems which are registered to your target. This is how you can do that. For example, for RIPE, you can do it for any other registry authority in North America, Asia, whatsoever. Get the list of autonomous systems they are running, and then there are not a lot of services which you can use from. One is from Hurricane Electric, for example. You can just dump what IPv6 address spaces are they actually announcing. So this is the address space RIPE is announcing, and that is what is reaching their systems, so their networks. Everything else they have to register, it will not reach them because it's not announced on BGP. So this is the best way to find out which is the actually used IPv6 address space of a target company. So we see here one AS. The first AS has one address space, /48. They have another 48 on a different AS. And the third one has no IPv6 prefixes now. Of course, IPv4 prefixes, but no IPv6 prefix. The fourth has a lots of IPv6 prefixes. And if you see, they are all /48, so it's something like 20/48 networks. This is an address space that is very, very, very large. So we come up with such many large networks. Again, very hard to cope with that because the address space is very, very large. And it will not have millions of alive systems, just some. And find these in such a large address space. So there are ways we can handle that. The first is we must find out which networks are actually used from these large possible network address space. In my research, you can see that also from my second installment, there are IPv6 addresses which are more commonly used than others. So in 63% of all networks I reviewed, and this is a statistic based on 8,200 networks, the ::1 IPv6 host address is configured, and you can ping it, so you can reach it. This is usually the main router in that network. Then 76% have ::1 or ::2 accessible, so ping, TCP to SYN TCP packet to port 22, for example, stuff like that. And 79 of the networks you can detect if you scan 0, 1, or 2 as the whole part of the network address. So what we can do now, we just scan the host parts, 0 to 2, which are used over 70%, so in over 70% of the networks that are reachable, and scan the /48 network prefix, every network prefix we find. So in just 30 seconds, we can do this for every /48 prefix, which is pretty fast, gives us over 70% statistical average used networks, and these which came up, for example, for this prefix here. And then we know, okay, this network is used, this network is used, and this network. So 3 networks of this IPv6 prefix address space is in use. Maybe there are more, then we didn't find them because we are only looking for these IPv6 addresses, host addresses. Yeah, but in IPv6, you must be lucky if you find something. Again, this is what I found out gives you the best coverage. The next source of information is actually DNS. Because IPv6 addresses are so long, so really so long, nobody can memorize IPv6 addresses. So all the information to connect, so administrators can connect to their systems are in the DNS. So the DNS is a vast resource for you as an attacker. So getting everything possible out of DNS is essential. Sadly, the reverse DNS entries are usually not as vast as the host to IPv6 address resolution. However, you can find lots of stuff in there. I would call it a feature in the DNS standard, how DNS works, that you can ask for a DNS entry. So this is just part of an IPv6 host entry. And then from this, we add 0.1.2.f. And if this subdomain exists or not exists, you get a different kind of error from the DNS server. So if there is nothing like 0.8, whatever IPv6 address, you get an NX domain error. If there's something underneath this leaf, you get a no error result. So you can walk the whole address space for the target down until you come to the full PTR entry for the reverse lookup of an IPv6 address. And this works in seconds. So thankfully, this is how it works for RIPE. You just ask their main DNS server, hey, give me everything from, let's say, from this network address space, which are you responsible for, and then you see, yeah, thank you very much. And this gives you IPv6 addresses which are very likely in use. If you can reach them, because there might be firewall in between, that's a further step. But now you already know, okay, these are possible addresses. And also very important for later, you see their host numbering scheme. For example, here you can see for these types here, they always have C100, and then they're counting upwards the address space. So this is, if we see that, we can use this information to further enumerate their numbering scheme to find more systems later. For the other DNS information stuff, you can do zone transfer. This always gives you the full picture of what's in DNS, but okay, sadly, this rarely works. If they have DNSSEC, you can, and they're not using NSEC3, then it's way more complicated, because then you have to get hashes, you have to crack the hashes. It's possible, but pain in the ass. If they have the insecure NSEC deployed, then you can just walk every entry in DNS. So you just let your tool run, and it dumps all entries in the DNS for you, if they have DNSSEC with NSEC and not NSEC3. If they still not work because they don't have DNSSEC, then you can still do DNS brute forcing. So let's do it all with RIPE. Because, yeah, surprise, surprise, RIPE allows full zone transfers of the DNS. Again, something where you think, okay, it's not 1985 anymore, guys, please. So everything, their internal naming scheme, their address scheme, you see everything in there. DNSSEC walk, yeah, they're using DNSSEC, of course. They are one of the driving forces for DNSSEC, but why do you deploy the insecure NSEC implementation instead of the more secure, well, still stuff you could do, but the more secure NSEC3 one? I don't know, maybe because they want me to do this presentation. They want to support me, maybe, I hope so. So this is how you can get every information out of DNS through DNSSEC walking. And if this fails too, then the only possibility left, but that always works, you just guess possible host names. And the tool which is all the tools you see here are in the IPv6 attack suite, which is out there for 7 years already, and the newest update is available already on the THC website. So all these tools are already now available for you. And this already comes with the dictionaries, which is over 3,000 entries, large, real-world statistic data based on the entries there, so it is really an effective list. And again, you see these are the host names and the IPv6 addresses behind that. This gives you, all in all, lots of possible alive addresses. So you have from the DNS, you have from the prefix scanning, you have networks and hosts which could possibly reachable, could possibly be alive on the network. So with the tool Alive6, you can now check if they're alive. It's a kind of ping scanning tool, but has more alive checking techniques. So TCP, well, let's go through. That is how you would use that. So I'm really trying to help you here step by step through if you ever want to do that. You should put all the systems you found, all the networks you found into one file, and then just put this as an input file for this Alive scanning tool. With the capital D parameters, you scan for common addresses in each network that's found. So if you have you found 20 possible IPv6 addresses in 3 different networks. For these 3 networks, common, often used IPv6 host addresses are being enumerated and tested. Capital M means there is I already told you there is something like auto-configuration. Auto-configuration is often done based on the MAC address. So if you found one system in the DNS which has this auto-configuration based on the MAC address, you can enumerate the rest of the vendor ID address space. So if, for example, they had one Dell server doing auto-configuration in the DNS, and they might have more Dell servers, this option does that automatically for you. Capital F is firewall piercing mode. Normally, the tool just sends ping packets. With the firewall piercing mode, it sends TCP SYN packets to various ports, a UDP packet to port 53, a TCP ACK packet to some high port, an ICMP error packet, which can also generate a result. So it tries to get through firewalls, but you can also find grain mode with more command line options. You just send it, and then, yeah. If you do it for all the addresses I found for RIPE, and again, they have a firewall, as I saw with some stuff. They never complained. They seem to be happy to be a leading example on how not to do things. You'll see that from the internet, over 670 systems are reachable in the RIPE network. And I don't think this is a secure sounding number. Yeah. So the next step after you know, okay, these are reachable IPv6 addresses is standard pen testing, port scanning, service enumeration, attacking the services, et cetera, et cetera, et cetera. So this is how you do pen testing IPv6 networks. As I said, the first time ever it is shown how this actually has to be done. It's not rocket science, but it takes quite some stuff to get it all together. For local host discovery, so if you're attacking internally in the internal system, the internal networks, this is already partially documented on the IPv6 hackers mailing list. Because of time restrictions here, I haven't put it in the slides. They're already, for the local discovery of systems, there are already Nmap modules for that, so NSE modules. And it would be very nice if someone would put everything together, like my live tool, other stuff I have here, if someone would write Nmap modules for this as well. Because I love to have one tool which does everything. Yeah. So you can even do nice network maps. I don't know if RIPE is happy to show people this is how the network is structured, so you see all the networks and how they are connected. This is stuff you can do if you have that information. So, okay, 8 minutes left. Wonderful. I want to talk a little bit about the problems we have in IPv6, why it is so, how do you say, frustrating. I don't mean actually from a security standpoint, but from an administrative standpoint. You might think deploying IPv6 is easy. Actually, it's not. Because in IPv6, there are a lot of political battles going on. For example, auto-configuration was designed from network people to get rid of DHCP. Why? DHCP is run by usually the Windows server team, but not by the network people. Yeah? And it's also not nice to have an upper layer protocol, so UDP protocol, being responsible for low-level network stuff. Yeah? So that's why auto-configuration was designed to get rid of DHCP. The problem is, as they found out way too late, they forgot to implement the feature to set a DNS server. Without a DNS server, what do? You need a DHCP server. Otherwise, you can't configure a DNS server on the machine, unless you want to manually configure it for all machines. Well, good luck with that. After quite many, I think it took them 7, 8, 9 years to realize it and then come up with an RFC. Now it's a problem, nobody is implementing this RFC. So basically, auto-configuration, which could have been a very cool feature, is kind of dead. On the other hand, if you say, okay, then we do DHCP version 6, we're using DHCP version 4 already for a long time, we have the experience, it works, so let's do DHCP version 4. Well, when they defined auto-configuration, they wanted to make sure nobody is using DHCP version 6. So intentionally, they put trouble in there. You can't configure a default gateway via DHCP version 6. You can't configure route entries via DHCP version 6. And if you do uninstalled installations of system on IPv4 via DHCP version 4, so you know the MAC address of the device, it gets a special IP address, special configuration by DHCP, so it automatically installs software on the first time the system is booted up. This doesn't work with DHCP version 6 either, because this is not allowed. The standard requires you use something like something called the DUID. This is a value or a unique ID for a system which is generated the first time it's booting up, because it's also based on the time the system is first booted up, to not have collisions and stuff like that. This means that some initial, you never booted up the system and automatically have system installed. This is not possible with DHCP version 6 anymore. So people are not happy with auto-configuration. People are not happy with DHCP version 6. And not every system supports DHCP version 6. For example, there is no plan for Android on the roadmap to have DHCP version 6 support. Yeah? So pretty much, if you are in an environment which is very mixed, you are fucked. Sorry my language. If you lost 2 world wars, you kind of get grumpy with the world. So this is something which is really troubling if you want to deploy IPv6. Then there's other stuff. You have lots of security issues. I showed you some here. There are security features in switches and routers you can deploy to somehow reduce that risk. The problem here is, however, that to get the even kind of the feature parity, like DHCP snooping, ARP inspection, and stuff like IPv4, for IPv6, you pay twice to 4 times the price for the switches and the routers. There is some reason for that. That is that IPv6 is a way more complex protocol, and therefore way more ways to bypass these protection mechanisms, as I showed 2 years ago. But it needs more CPU power, it needs more RAM, so it's higher class machines. That's why they are more important, more expensive. But that means if you wanted to have the same security, but at least some more security on the IPv6 network, so at least get a little bit to the insecurity of the IPv4 networks, that means that you have to pay more money. And we know how much this is something management likes to do, throwing more money at network equipment. And then next thing is vendors don't seem to care. If you ask me, who has the worst IPv6 support from a security standpoint in the operating system, surprisingly, it's not Apple with OS X. No, actually, I don't like Apple, but they're getting better and better. It's also not Solaris. Nowadays, it's owned by Oracle. You might expect that. Adobe, it could be Adobe if they would be responsible for an operating system, but no, it's Microsoft with Windows. They know about issues in their IPv6 implementations. This is the company that says IPv6 on your system. How does this work? Bugs and saying, yeah, but if you want to do something about it, you're fucked. Yeah? So this is really, really bad behavior, and Microsoft tools itself to be one of the drivers for IPv6. So what I can say is shame on Microsoft for that, not fixing the bugs, not taking responsibility and doing good things for IPv6 security. So that's it. Here you can download the tools. Maybe they can get IPv6 support enabled again here for the network, and you can have lots of fun, I can promise you. Contact, if you ever have a question about IPv6, please, security related, just email me. I guarantee you get an answer if I can read your email. Yeah, sometimes I get emails you wouldn't believe. Thanks for people who, like me, give out stuff for free. So I give my tools out for free for everybody. There are people who make very nice pictures, make them available for the internet for everybody to use for free. Thank you to these people. Thank you for staying here, because I know it's the last sessions when people are tired, information overload. I try to remove more of the technical stuff, make it a little bit more entertaining. I hope you had some fun. And now it is time for questions. Yes. This guy I've never seen before, and
hey, thanks for the presentation. I have one remark and one question. The first is about the difference in filtering between IPv6 and IPv4 that you showed. And you basically say that people are not filtering IPv6 because they think it's secure. Given that stupidity is far more common than evil, don't you think that is more related to people forgetting to actually filtering IPv6, which is very common in pen testing world? We know that for years, that scanning IPv6 is more efficient when it's activated. And then the question about the RIPE. So you're basically scanning about 50,000 machines, and you find 0.1% of these machines.
No, I'm sorry, I'm not finding 0.1 machine, 1% of the machines. I'm scanning a very large, very small address space of the whole possible address space. No, but because of the DNS information, I can pretty sure that I have discovered 95% of the real machines that are there.
Okay, but
from that gigantic address space. That's what it's all about.
But the way I understood your slide was that you had 50,000 names, and you scan them, and you get 700 replies. But my point is, did you compare it with what was accessible through IPv4? No. To see if it was, because maybe there's a legitimate reason for these 700 machines to be actually reachable.
Very likely. I totally agree, but that's not why I put RIPE here. I didn't want to say, oh, on IPv4 they are secure and therefore get IPv6. That's not what I wanted to show here. So please, that's not what I wanted to tell. What I wanted to tell is, this is how you do this for IPv6, and to see if this technique works, this is how it works. Yeah, and it works at RIPE. I didn't want to say, oh, IPv4 is secure, IPv6 is insecure. Just, if you want to try out these techniques, this is how you do it, and you can try it out for yourself. And yes, I found more DNS entries than I found a live system, but that's they have firewalls. They have firewalls which prevent me accessing a system. I know it is very likely it exists, but the firewall prevents me accessing it, so I can't scan it. Yeah? So for me, for pen testing, it's important to attack these machines which I can reach. I can't attack a machine that I can't reach, obviously.
No,
Yeah?
I see your point, but I don't see the relationship with that number being big or small or related to IPv6 vulnerability, as you said when you presented the slide. That's just my point.
Well, I hope everybody else did. Sorry. One more thing when you said, yeah, people forget, so the differences between IPv4 and IPv6 protection on the routers and the servers, actually it's two reasons. One is, very correctly, people don't think about that IPv6 is a different network stack, so it's different kind of filter rule. So your IPv4 filter rule, deny all, doesn't hit for IPv6 packets, so people forget that. That's one reason. The other reason is that the firewalls they have in place are not supporting IPv6. And I think they have problems with management getting the budget for an IPv6 firewall, or they have to deploy, and let's say the trouble to finally get an IPv6 firewall, I mean, you know how it is with larger companies, takes a long time for ordering, getting it delivered, and finally setting up it in the data center. It takes a long time, yeah? And until they already have IPv6. I think that's the second reason why there's this difference. Any other question? Everybody seems to be tired, asleep, in a coma. Did my job. Yes, please?
When you said like 1.8 seconds...
There's a microphone, please.
Wait, thanks. When you said 1.8 seconds from Japan to your host in Germany, did you compare that to IPv4 ping, LTT?
No, I did not, because let's say you do a DNS resolving for a host name, you get back an IPv4 and IPv6 address. You never know it's the same system. It could be on a completely elsewhere in the world. So unless you really have access to the system, you can check the address configuration, you would never know it's the same system. Yeah? So I didn't. For me, important was just, oh, with a router alert, I get that much faster. But if you compare the general, well, for some systems, you know it's the same. And if you do, for example, FTP to the systems or pinging the systems, you will notice, the more you work with IPv6, that the IPv6 network is faster than the IPv4 network. Just because less data is traveling on the IPv6 network, the hardware is newer, the routing and the performance of the router is better for IPv6 than it's IPv4, although the maximum data you can send in IPv6 packet is 20 bytes slower than compared to an IPv4 packet. Yeah? So a little bit less of data, maximum data can be transferred via IPv6 per packet, but latency, travel speed, and stuff like that is way better on IPv6 than it's on IPv4. So if you have larger downloads, do them via IPv6. Okay, we're already over time. Thank you very much. If you want to join me for a beer later, yeah, I'm here.
Thank you very much.